what we want to do is introduce another concept, is if the second law efficiency for devices weren't sufficient, there's adiabatic efficiencies as well. And the adiabatic efficiencies apply to turbines and compressors. And this efficiency is actually the one that tends to be used in industry more than the second law efficiency. So let's examine what it looks like. So I'll take a turbine. So we have a turbine. We'll have a slightly different information of how we label them. So this is the turbine work. Enters at state 1, leaves at state 2 prime. So I'm going to use 2 prime as the actual state. And I can represent this on a TS diagram. So I'm going from state 1 to state 2 prime. So state 2 prime is just as we had used before for the actual exit conditions, but now we want to have an isentropic state as well. And so what this is we're going to say H2S. And 2S would be the isentropic or ideal state. So state 2S is ideal, reversible adiabatic, expansion. And so what the challenge here is, when we were looking at the work potential, if I looked at the second law efficiency, and we'll examine this in an example in a little bit. When I look at this, this is down at the exit pressure. And typically, it's for a turbine, it's your exhaust pressure, and you can't use it anymore. And the second law efficiency says there is still work potential associated with this, engineer, figure out how to use it. This one says, engineer, design something that uses all the work potential. You're going to have a reversible adiabatic expansion. There are no irreversibilities. Do that, and we're holding you accountable to this. So the adiabatic efficiency, eta sub t, is equal to H1 minus H2 prime. And this is the work, so like Q plus H1 is equal to WT plus H2 prime. So WT is equal to H1 minus H2 prime. So we've done that a million times. So this is that, and then the work, it isn't work potential, but the best you could have done is had it be a reversible adiabatic expansion, H2S. So this is your adiabatic or isentropic efficiency. So sometimes they're called isentropic efficiencies, sometimes it's called adiabatic efficiencies. And so this is for a turbine. We can do the same thing for a compressor. And in this case, a compressor obviously compresses, and we're going from state 1 to state 2 prime, and we're putting work in, WC. We're going to have it be adiabatic. And so I have Q plus H1 is equal to WC plus H2 prime, or WC is equal to H1 minus H2 prime. And what we do when we write the efficiency, this is a negative number because it starts at a low temperature and goes to a high temperature and pressure. So what we do is we write this as a positive number. If I look at the TS diagram for this, so we're going from P1 to P2. We're starting at state 1, going to state 2 prime, and this is the actual conditions. And now what we do is we say H2S is up here, H2S, or state 2S, and then the adiabatic efficiency is the ratio of these, the actual and the ideal. Eta sub c is equal to H2S minus H1 over H2 prime minus H1. So this represents the actual work it took to get to P2. This represents the reversible work, the least amount of work necessary to get there, and so your adiabatic efficiency relates to that. Now I'd like to look at, there's an example problem, 9.8, that looks at a turbine. I'm going to do a different problem for a compressor. So example 9.8 does eta sub t and eta sub 2 for a turbine. We'll do an example problem for a compressor. And this is problem 939. So we're going to have a compressor. It's going to be an air compressor. It's going to receive 15 kilograms per second of air. Q dot is 0 is adiabatic. It's 20 degrees C, 293 degrees K, 60 meters per second. So we're introducing velocity in this case. It discharges at 400 kPa at 433 degrees K, nothing like writing on a crack, and 98 meters per second. And we want to find the power, the change of availability, the second law efficiency, and we'll find the turbine efficiency as well, the adiabatic efficiency. So with this, our first law analysis is Q dot plus N dot E1 is equal to W dot plus N dot E2. And so we're using E because we have the velocity as well. So we have, and Q dot is 0, so I have W dot is equal to N dot E1 minus E2. And now we can put in these terms. It's equal to N dot times H1 minus H2 plus V1 squared minus V2 squared over 2,000. And so this is C sub P, T1 minus T2. So I have W dot is equal to 15 times 1.0047 times 293 minus 433 plus 60 squared minus 90 squared over 2,000. And so I have that the power is equal to minus 2143.75 kilowatts. So it's a lot of power. And so anyway, this gives us the compressor power. This is the power that's going in to make this work. And now what we're interested in doing is we're going to be finding the change of the availability of the air as it goes through it and calculate the second law efficiency from that.